start. I think we'll let people keep on joining, and so welcome for this class. And then today what we plan to do is we'll basically discuss all these criteria for fatigue. How do you basically predict whether it will fail or not, and if you have any load distribution. So if you have alternating and a mid-range stress, if you can quantify it, how do you basically predict what kind of failures would occur? And then also what I would like you to understand is how do we, in case, what is the factor of safety, and in case there is no factor of safety, what would be the finite life for it? Both things we will cover. So that's what we have planned for today. So first thing what we want to do is we want to identify what are the key things which some of the key criteria which we use in fatigue modeling. So the first thing what we do is, the simplest one is, if probably you would have seen that, is and it's a very conservative estimate, Soderberg criteria. The second one is Goodman, and these are very old. These are pre-1930s, very old criteria for fatigue. So people understood that there is an issue with fatigue, and then they tried to incorporate it in various models. So first was Soderberg, and the second was Goodman. We'll tell you what exactly it is. And then people tried to, and these are fairly conservative estimates, meaning they have an additional level of safety in this via this model. Then the third one is Gerber. Gerber passes through data. If you have data, you basically have a best fit data, and this is the Gerber line, if you see. And then people, what people figured out is that there is another way to do it. Just give me a minute here, I think. Yeah. Okay. And then they used there was something called ASME elliptic. ASME elliptic is the latest one. What it does, it actually improves the Gerber one. It has data, and it actually also does the yielding check. So I'll explain what I was trying to show here is that any loading condition, right? What will happen is if you take say Soderberg or Goodman or any criteria, I'll take for simplicity. Let's say what is the Soderberg. So basically this line right here, SE and SY. Let me actually highlight it. I'll use some other color to show you. Inking color, pointer option, ink color. I will make, let me do green to begin with. So this one is the Soderberg criteria, right? This one, which has yield on one direction and endurance limit on the other direction. This is Soderberg, right? And the other one, let me change the color again. This one right here, the red one. This one is modified Goodman. This is Goodman. Right. So if you see what happens is, if my combinations of say sigma A and sigma M axis are there. This is the sigma M axis, and sigma A, if you remember, sigma A is, can somebody answer me what is sigma A? How do you get the amplitude component of the stresses, or the fluctuating stresses? Start to use your chat boxes, or you can also talk to me. Anybody? How do we calculate the? Yes. So amplitude is sigma max minus sigma min by 2. And mid-range is sigma max plus sigma min by 2. So this is this component. This is the other component, right? Sigma and sigma m. So if a combination of sigma A and sigma m is say somewhere here, we have a factor of safety. So this will be called This is called load ratio. This line is called a load ratio line, the line which I have just drawn. And here it is safe because if you see, this is where the fatigue will occur. And you see that there is an intersection point. Let me just go ahead and show you a very interesting thing, which we discussed last time also. If you see, there is this Langer line, which is yield line, right? And then there is this is the Goodman line. So if you see, Soderbergh line actually is a very conservative line. So Soderbergh is actually, it will always fail. If I use Soderbergh, I am actually overestimating the failure. So basically, I'm over designing. So, but then say this is the condition for, this is the line which is there for Goodman. This is the line. Now, if I am here, if the combination of sigma A is very small, sigma A small, and sigma M very large, it will actually it will fail in yielding. This combination will result in yielding and not fatigue. So failure will happen in yielding, it will yield and fail. And the critical onset where with one combination is called first cycle yielding. So I have a combination of sigma A and sigma M right here. Let me just go ahead and delete that. If this point, if you see, if I have a sigma A of this and sigma M of this, you know what will happen? Is it right at the onset of yielding? So this is called first cycle yielding. So if I give a combination of sigma A and sigma M, which is right here, it will yield at first go. So this is called R critical. This is the critical ratio. And here, if I am here, basically means that the sigma A and sigma M combination would result in yielding. In the first cycle itself, it will yield when I give this combination. So this, anything beyond this, if you see the Langer line, sorry, this is not the right line. I wanted to see this line actually. I'm sorry. This line, this is the line. This is the line right here. This and this, where first cycle yielding will happen. So here, this is yielding. So and the fracture happens late. So yielding happens first beyond this point and fracture happens late. That's what I wanted to explain. Any questions here? Did you get what I'm trying to say? I'm saying that there's a combination of sigma A and sigma M where the first cycle itself will give you yielding. Is it clear? If not, I'll stop and ask me the question. I'll explain it and then move on to the next thing. Because today we'll do some real problems to basically identify what kind of factors of safety are there for fatigue life, for a general fluctuating load, not for what we discussed last time was fully reversible loading. Not for reversible loading, but for a fluctuating load, for real fluctuating load, which you will experience in most of the engineering conditions. Any questions here?
Did you shift the point from the first case to the second case?
Come
for
again?
the first cycle yielding?
No, so basically it will come from loading, right? My sigma, this is my sigma A and this is my sigma M. So if sigma max and sigma min combinations will give me sigma A's and sigma M's, right? So if that combination is right here, means it will be first cycle yielding. If that combination is here, means it will fail in fatigue, and there is a factor of safety. So factor of safety is basically this big line. Sorry. So this line, basically, if I'll show you this. So OA, here is my loading condition. Here is my final where my fracture occurs. So this is fracture of safety will basically be OB divided by OA. because I'm here and I'm allowed to go till here. This is where this is the so I'm actually so basically it means that I'm operating. So say I'm operating at this sigma A and sigma M combination, say this sigma A and sigma M conditions, right? This is sigma A which I'm operating because of my sigma max and sigma mins which I'm giving. I'm getting value of sigma A and sigma M somewhere here. So I'm still safe. But the moment I have another sigma, say sigma A1 and sigma M1, which is sigma A dash sigma M dash, which is right at this envelope, I have factor of safety of just 1. I am actually very close to being unsafe. Or in real say that it is just on the borderline of infinite life. If I go here means I have a finite life.
So do we call that first cycle fatigue failure?
No, first cycle fatigue, no, first cycle yielding. First cycle yielding is here. First cycle yielding is here is because up till from here to here, you see, it will always fail in. So yielding is much beyond that, right? If you have this sigma and sigma M combination till here, right? If I am till here, say imagine any sigma A and sigma M combination. Let me just do a better job of, I've scribbled quite a bit. So let me clean it up and then show you. So let me just first tell you that there is a transition here, right? Can you see that? If I see, so let follow the Langer line here. This is the yield line, right? This is the portion of Langer line which I'm talking about. So if I have something like this from here to here, if I'm from here to here, right? Any combination from here to here, or actually let me say not here to here, but any combination here to here, definitely I will hit this line, right? First. So that this line, actually this up till this line, this is because of fatigue. Now right here, if I have a combination of, say exactly this combination right here, some say some sigma A and some sigma M right here, which corresponds to this point, right? Then this sigma A and sigma M combination will result in yielding. Even the first time I get, on the first cycle which I get, there will be yielding, because sigma max will turn out to be equal to sigma yield. You get me?
Yes, sir.
So the sigma and sigma M combination will result in yielding even before it fatigues. First cycle, that this the combination of sigma and sigma M which corresponds to this point. And what happens is at this point, from this point onwards, when you hit this line, you will actually see yielding first. And fracture will happen later. This is the fracture line. This line is the fracture line. This is where it will fail in fatigue, fatigue line, fatigue failure line. But even before the fatigue sets in, you will see yielding. And whenever you design, right, you don't want yielding in your component also, right? So here what will happen is yielding is your limiting criteria and not fatigue. Here, up till here, your fatigue is the limiting criteria in this zone. In this zone, let me just say, actually, any combination here which will actually hit this line. This line is there you will fail in fatigue. But if you have sigma A and sigma M combination, so any sigma A and, so if I am here, so here I'm all safe. Actually, any combination here I'm safe, right? I am safe. But if I, so imagine I have this combination. So let's take two conditions. I have one condition here and the second condition here, right? So condition 1 and condition 2. I'm safe in both right now. But if I increase, if I aggravate, I will see yielding here. If I go ahead and keep on increasing sigma is and sigma, I'll hit yielding first. Here, if I keep on increasing, I will hit fatigue. It has infinite life till I go there. So this is this will be my factor of safety, because I have room from here to here. I have some room, right? I still have room to I'm still having infinite life. But if I go here, beyond this line, then as per my Goodman relationship, I have finite life. Have I confused you or have I answered the question? If not, just articulate and then I'll explain it again.
Sir, you answered it, but I was asking, so we have the first cycle yield line, which is the
Let
part
me
of the
just draw
Langer
that
line.
first cycle yield line. It is right here. This is called first cycle yield point. This the combination of sigma is and sigma m here. So this sigma a and this sigma m will lead to first cycle yield because you're hitting the yield line here. This is your yield line. Before that you have this line is fatigue line and this line is yield line. So there is a transition from fatigue to yield. So if I have this sigma and sigma m combination, if I increase something, right, here I am safe, but the moment I increase it, I will see yielding first. So my material will yield first before undergoing fatigue. And it will be more clear because I will actually show you real examples today. So don't worry about it. Let's just wait when we solve the real problems. So you'll have more clarity with some numbers. Okay. Okay. So that's what I wanted to tell you, that these are and there are multiple ways to predict. So we can use one method to predict something and the other one also to show which one gives you what results. Okay. So this is the relationship for first thing what I will do is I'll show you the actual all the relationships. So Soderberg is basically sigma a by SE, sigma am by SY. So see, this is very conservative. It assumes that anything but SY, this is better than that. This is instead of SY you have ultimate. So Gerber, if you see, takes into account this SUT. So it doesn't take account yielding, but it's actually fitting the data. So you have sigma A, sigma M, SE, and SUT. Okay. So you basically plot this with the data, this line, whichever you have. Okay. Now, here what happens is in ASM elliptic, you also check for yield. So these are the differences between these. So this is the most recent one, ASM elliptic. Okay. And this is the oldest one and most conservative one. Okay. And this N you see is the factor of safety. The factor of safety, I actually told you physically what it means is if you have, so let me just for simplicity, I will just draw this Goodman, modified Goodman. So this will be SE and sorry. Let me do this. So this is say SE, this is SUT, this axis is sigma M, this axis is sigma A, and this is SY, yield stress. So this is Langer line, and this is modified Goodman. So if I have a combination, if I am somewhere, say I am somewhere here, whatever my loading condition as per my physical thing, sigma max and sigma min, which I have in the loading cycle, say I'm here. So I am right here, but I can go up till here and still be safe. Right. So this ratio is my factor of safety from here to here. So if I say A and I say B, so OA, OB by OA, sorry. It is always more than one. It has to be always more than one. OB by OA. Right. So this is my safety limit. What if this is my factor of safety N, which is given here? And I can do this for any of those relationships. For simplicity, I showed you a linear relationship. but you can do it for either Gerber or asymmetric. Instead of straight line, you will have something like this. You will have a curved line. Right? Now, what if my n is 1, less than 1? Now tell me what does it mean? Somebody should type it or say it out loud. Ideally, for all my designs, this n has to be greater than 1, right? Then only I'm safe. But what if I do all this and find n to be less than 1? What does this mean? Any answers? Somebody? Expect at least one answer, right? What does n less than 1 mean? No, it doesn't mean yield occurs first. It actually means that you have a finite life. It may still fail in fracture, but you have, underdesigned is the right word, but it physically means that you don't have this 10 to the power 6. Infinite life is not there. You have a finite life. That's what it means. So basically meaning that if you are beyond the line, you actually fail in fatigue only. You fail in fatigue, but you fail earlier than 10 to the power 6 cycle. So you have a finite life. This line which you have, this line which I made, all those lines which I made, right? Those lines basically mean that anything below this has infinite life. Anything after this has finite life. This is finite. Right? So this is what I want to give, and I think you will have better understanding as and when we do a few more things. Okay, we'll do the problems. I think we'll have better understanding now. Let me just. Okay. So these are the equations for different conditions. There is something called load line. Load line, which I showed you, load line basically means is if I have sigma A and sigma M here, this sigma A and sigma M, this line which actually passes through it and the origin is load line. And there's a critical line. This critical line is where, for if I have to show for this, so basically if I have SE, SUT, and I have yield like this. So this line, this slope where first cycle yield occurs, this is R critical. So this is load line, this is critical line. Okay, wherever the first cycle yield occurs, this line joining the point and the origin where the first cycle yield occurs is called critical line. Okay, this will be more clear as and when we solve the problems. But you have to understand that the equations are slightly more complicated for Gerber and asymmetric. These two are linear. Sorry, my mistake. These two are linear. These are non-linear. That's the basic difference, and more accurate. Right. So I have explained a few things here. You can look at it, and when you solve problems, we will go back and look at these things. Okay. So commonly used for criteria is Goodman. Modified Goodman is linear, very simple to use for design, because I showed you I drew like 3 times here itself. It's very simple to understand and evaluate, but it is conservative than Gerber. So you're over designing, right? Soderbergh is even simpler, but it doesn't even account for ultimate. So it actually just fatigue and yielding. It has only 2 things which it worries about: fatigue and yielding, right? And Langer line is just yield. So you draw a line from yield to yield is Langer line. And now a fatigue criterion, rather than being a fence, it's more like a zone or band where the probability of failure could be estimated. So it's not a, it's not just one point thing, right? You are basically having some room there. So it's more like a band where you have high probability of failure. So you should not understand that this is like this answer is unique, because you already have like 3-4 criteria, and each criterion will give you some different answer. But the question is that you should be, when you take into account all the things, you have covered your bases, and you can be sure with certain degree of confidence that the probability of failure will not occur within this. So it's still not a very deterministic way. Although we use the model as deterministic, you should not consider this as a deterministic model. There is still outside chance that it can fail even when you have designed like this, just to be clear. But the probability is very low, right? So that thing you have to keep in mind, that these are very probabilistic, right? These are not unique deterministic kind of models. And the failure criteria of Goodman has certain advantages. It's very straight line. Algebra is linear and easy to be graphed. You can actually do graphical solutions and reveal subtleties of insight into fatigue problems. And analysis can be scaled from the diagrams to check on the algebra. So we'll actually solve a couple of problems today, and then we'll see. We'll do Sodernier, we'll do Soderberg, not Soderberg, we'll do Goodman and elliptic as well as Gerber. All of them we'll do, and then we'll see how easy or how difficult it is, and how the answers are different. How different are the answers? Intersecting slope line with each failure criteria produce design equations. So these are your design equations for Soderberg, modified Goodman, Gerber, and LSM elliptic, which we'll use quite a bit. And the factor of safety for modified Goodman is this. For Gerber, so Gerber is this. These have been solved. Equation you solve, and then you'll get your we'll show you both graphically and using these equations, and elliptic and Langer failure criteria. But we actually do all three are tested against Langer failure criteria. Okay, because there is a critical line. Above that critical line, most likely you will have a fatigue failure. Below the critical line, most likely yield would occur. So this is a simple problem. Let's take it from there. You have a 40 millimeter diameter bar, which has been machined from ASI 50 cold drawn bar. This is witnessing a fluctuating tensile load. So I have a tensile load which is fluctuating between 0 to 70 kilonewton. Because of the ends, it has a fillet radius. So it has a 1.85 of concentration factor. First thing what we have to do is we find SA, SM, and factor of safety against fatigue also, and first cycle yielding also. So you have to do both Gerber and ASME elliptic fatigue line. All you have to do. Okay. Now how do we go about doing this? Can somebody give me some idea how do we go about doing this? First thing what we should do. What is step one? If I see this problem, what do I do? What is the first thing I should do? Some answers? To do anything, what do I need? Yes, very good. I need to find sigma A, sigma M, and SE, which is endurance limit, right? So how do you find these three? At least I need to do for the very first thing, and determine other properties also. Determine other properties such as SUT, SY. I need these properties also. For ASI 1050, AISI 1050, cold drawn bar. So the first thing, let me just go one by one. We'll go one by one. Solution step. First thing I would like to have is, let's find SY and SUT from data. So how do I go ahead and find SY and SUT from data? Look at the table in the end. So if you just give me a minute, what I will do is I will flip the screen and I'll show you what data we have. I'll share the screen. Okay. So let me start with this. First thing what I would need would be let me just go to that appendices. A20, right? I have the material which is AISI 1050 cold drawn. This one. Sorry. Shoot. Okay, this is the thing. I'm not able to pick it up rightly. Yes. So these two values, 690 and 580. Okay. So basically, I have so I find out what will be the tensile strength. I'll use SU2 and basically SY. So 690 and 580. Okay. That's the first thing we do. Next thing, what do we do? Okay. So first thing we figured is we do. Looks like there is a phase lag between this skin. Yeah. The thing is we need to. So now I have the data of SY and SUT. That's the first step which we have to do. The second thing is I have to find the fully corrected endurance limit, because I know that my actual endurance limit would be zero point 0.5 times whatever this thing is. If it's less than 700 MPa, it's 0.5 times the so my 690 is what is it? It's 0.5 times SUT. So 690 divided by 2 is basically my if I go ahead and find my SE uncorrected, sorry, here, yeah, here somewhere, my SE uncorrected, if I see SE dash, if I see my uncorrected SE is 0.5 SUT, right? But I have to have some modifiers for that. Okay, so let's now find the correct. Second step is, let me do this. Just 1 second, I think it will be more clear to you. Okay. So I have to find the modifiers for the endurance limit. Okay. How do I find the modifiers? What do I go ahead and do? Which is the first modifier? I'll just go ahead and share this thing back. I'll stop sharing this one and then go ahead and share the other screen so that will be clear. And then I'll come back here and do some computations. Can somebody tell me what are the things which we have to find out? What are the modifiers? If you remember the previous term. What other modifiers do we have? Just 1 second. Yeah. What are the modifiers? No, but surface modifier. So let's, very good. Surface modifier is 1. So if you remember, I'll just keep on going one by one. Shape, size. So I'll just keep on going one by one, and then we'll find the values for that. Very good. Let's go ahead and do all these modifier business, because I need to correct the endurance limit. So first thing would be surface modifier. First one, right? What is in this case? What is what do I have? What is the what kind of factors I have to use? Ka is equal. Sorry, K is equal to what do I have to use? Sorry, just go ahead and. So Ka is equal to, there is a factor A SUT raised to B. Now what will be the, it's a machine thing, right? So in MPA, A is 4.51. Our SUT we found out from the chart just now is 690, right? And B is minus 0.265. So this will be my K for this condition. It's a machine thing. So I have to basically account for what will be the modifier because of surface roughness. So first one, surface modifier, K. I found K, right? What is the next one? What is KB? Now, what will happen in the KB? Size factor, what do we do? What will be the size factor here in KB? Will there be one or no? Will there be a size factor or no? What will be KB? Any answers? So KB, if you see for axial loads, an axial loading, right? So the size factor is only for torsion and bending, right? So axial load KB is equal to 1. So I found K, I found KB. Let's go find KC, load factor. What will be the load factor KC? Axial load, so 0.15. So I found KC. What is the temperature factor KD here? What will you use? Any answers? So it doesn't say it's high temperature, it's room temperature. So I say KD is equal to 1. Reliability factor, again, it doesn't say anything. So let's assume that we design it for 50%. If it actually says that, okay, I want 99.9% reliability, then I would have used that. It doesn't tell me anything, so I'll use 1 for KD also. And miscellaneous factors also I'm ignoring because it's not mentioned explicitly. So I have Ka, Kb, Kc, Kd. All these are there. So basically I will go ahead and modify this SE. So SE dash is equal to what that number was, K, whatever K was 4. What was that thing? Okay, I'll just go ahead and read it out for you because it was 4.51, and then SUT is 690. 4.51, 690 minus 0.265. Okay. Times 0.85 times 1. So this is KB, this is KC, and remainder would be 1. KD is equal to 1. KA, KB, KC, KD is equal to 1. And K is equal to 1. So it doesn't matter. Then it will be 0.5 times SUT. Do the math. And this will give me the SE dash. This is the corrected, this is step 2. This is the corrected endurance limit. Now determine the stress components and correct them for stress correction factor. That's important because there is a correction factor. So I will basically find out without the base sigma AO and sigma MO and multiply KF to both. If you go ahead, I'll show you why this is done here. If you remember this fluctuating stresses. So KF should be applied to both alternating and major stress components. If you remember this. So whatever is the base sigma A and sigma M, I go ahead and multiply KF to that, and that will be my final thing. Okay. Okay. So now I have. So first thing I did this. Step 1 I did. I find out sigma SY and SUT. The second thing I found out all the modifiers, right? And then third, I found out what will be the stress components and correct them for stress concentration. So how do I find out what is the stress component? Default stress component, how is that? How do you find my sigma AO and sigma MO? So what I will do is, I will actually go ahead, my sigma max and sigma min. My sigma max and sigma min, if you see, my sigma max, my sigma max is equal to 70 times 4 divided by pi d square, right? And sigma min is 0 by 4 pi d square, right? So sigma max I know, and sigma min will be 0. Right? So I have sigma, and then what I do is I find out sigma A0 and sigma M0 from here. Sigma M0, sigma A0 will be sigma max minus sigma min by 2, and sigma M0 is equal to sigma max plus sigma min by 2. These are the numbers. And then I multiply it using 1. So basically, let me do one thing. I would go ahead now and I would actually use Mathematica to solve this, all these numbers, and then we'll go from there. Right? So let's see. Let me just blow Mathematica up a little bit. So these are my numbers. Let me go ahead and do. Plus. So I know SUT is 690, SY is 5. So basically what I do is I know KA is 4.5 SUT, 0 to 2.65, KB is 1, KC is 5, KD is 0, 1, KE is 1. And I go ahead and do everything and then find out sigma max is 4 FA by pi d square. FA I have also defined as 70,000 newtons, or 70 kilonewtons. So I'll get all these. Let me just clear first here all the variables. So I have Ka as 0.798, which you can see. And then the other thing which I got, SE is 233.948. This is the corrected SE. Otherwise, what we would get will be 690 by 2, right? Which is 345 or something, right? 345. But instead of 345, because of the modifiers, you have 233, right? So now I have SE, I have sigma max and sigma min. So I can find out what will be actual sigma A and sigma M, which will be, this is sigma A0, this is sigma M0. And I have this KF of 1.85. So basically, for all practical purposes, my sigma A and sigma M turn out to be, let me just go ahead and do this. My sigma A and sigma M turn out to be 51.5264, 51.5264. Now I have sigma A and sigma M. What do I do next? I have to find out what will be the factor of safety. So for given loading condition, so for this loading condition, I have sigma A is equal to 51.5264, 50 and 51.564. So I have all those numbers, right? So basically, now what I do is, let me go ahead and show you how the Gerber line looks. Can you see the Gerber plot right here on the screen? Okay. Right. So now what happens is I have, this is my sigma A and sigma M, which is 51.52. Sigma A is equal to, sigma A is equal to 51.52 and sigma M is equal to 51.52 MPa, right? So I have sigma and sigma M. Now what I want to do is I want to find out factor of safety. So basically, if I use Gerber, so this is the Gerber line right here. The curve, this is the Gerber line. This is the Gerber line. And if you know the equation for the Gerber line, I'll just go ahead and show you the equation so that, so factor of safety for Gerber line is this. Gerber line, so this is the factor of safety, this equation right here. I have SE, the modified SE. I have sigma A now. I have sigma M. I have SE. I have SUT, sigma A's, and I can find out what will be the factor of safety. Let me just show you what is the factor of safety. Just 1 second. So the factor of safety, if you see, this is the equation right here. And I know my loading line, the loading ratio is sigma A by sigma M, I showed you there. So I have this, and the factor of safety basically is 4.112, right? And if I want to find out, so let me just show this. So this is where I am. My loading condition is right here at A. What I have found out is OB by OA is 4.11. And the intersection equation, if you want to find out what is the intersection equation between the load line for a given load line and Gerber line, is this. Let me just go ahead and show you what the equation looks like. If I want to find out here. So if I have this load line is SA by SM, I know my load line here. For ASME elliptic, I have Gerber, right? So Gerber is which one? Sorry, So this is Gerber. This is Gerber. So this is my equation. So the intersection of my load line and the Gerber equation, this equation, if I solve these two equations, this is the intersection line. So I know SA is this. So these are two equations. The intersection between these two is given by SA this and SM this. So let me just go ahead and show you what do we get out here, and then we'll check whether our answer is correct or not. So now my SA is, if I go ahead and find out where this line will intersect. So this SA basically is nothing but this point right here. This point is what we have found out. SA is at B. So whatever we are finding out here, this SA is the intersection between the load line and the Gerber line. Right? So let me find out what will be the SA. Oh, sorry, I haven't defined R. So let me just go ahead and define the R. I'll run this again. 211.887. Now from these numbers, can we find out what will be whether 4.11 is correct? So basically, if I divide, so I'm saying that the factor of safety is nothing but OB divided by OA. Right? So OB is 211.9. OB is 211.9 and divided by, so basically, if I do 200 SA divided by sigma A, by sigma A. This should be same as my factor of safety. Let's just check. It should be 4.11, right? So I can also see it graphically. So graphically, I can see that this is, what does this mean? So basically, let me go ahead and share this one now. Okay. So I have found out this location, this SA. So this is my SA. I can find out SM. So SA by SM is equal to R. So I know R is 1. So SA and SM is also. So this is 211.9. 211.9. So this is where we are right now. This is where we are. And this is my factor of safety. So basically the factor of safety is OB by OA. So this much room I have. 4.11 factor of safety I have. So I'm safe. Here, I will have infinite life. For this combination, I will have infinite life. I will have infinite life. Okay. Now, if I have to find out where the first cycle yield will occur, how do I find it? First cycle yield will occur. I have to find out the intersection of this point, intersection of my Gerber line and my critical line. And then how do I go ahead and find that? I have an equation for that also. That equation I'll show you. The equation for that, if you want to find out, is this, the critical. This is the equation. Sm is equal to S square ut Sc. This is the equation. I solve this and then I'll find out what will be Sm. So basically corresponding to this Sm, if you go ahead and solve it, you will get 442 MPa. We'll get 442 MPa. If you want, I can just show you right here. Just 1 second, I'll just show you right here. So this is the equation which I'm solving. This is the intersection between, this is the intersection between this line, this is the D point. What is the Sm corresponding to the D point? So let's find out what is the Sm corresponding to the D point. So basically you go ahead and find out here. $442, and this is what we showed in 442 right here, right? And SA I can find out if I find out R critical, and R critical. So I have to find out R critical is Sm by SA. So R critical also I have to find out, and the way I can find out is Sm, this line Sm plus SA is equal to Sy, because this actually lies on my yield line. So I can basically find out this would be S. So basically my Sm I have, so SA will be equal to yield line, which is Sy Sy minus Sm. Let's find it out. What will be my Sa? 137.9. Because this lies on this line. This D point lies on this line. The equation of this line, this Langer line is Sa plus Sm is equal to Sy. Right? If you go ahead and see, the Langer line's equation is what? The Langer line's equation, if you want to go ahead and see, the Langer line's equation should be, the Langer line's equation is, this is Langer line's equation. Sa plus Sm is equal to Sy, right here. Let me blow it up, I think it will be more clear. So Sa plus Sm is equal to Sy, and this lies on Langer line. So Sa plus Sm has to be equal to Sy, right? And then I can find out, what will be, and then I can also find out what will be the critical line. This line, the slope of this line. The slope of this line will be Sa by Sm. So this should be equal to, let me find out. Let's go back here. This should be equal to Sa by Sm. It should be equal to, no, sorry, let me capital Sm. So let me just go ahead and do this, and I'll find out R critical. So R critical, R critical or slope of this critical line is equal to 0.311. So slope of this line right here, slope of this line is 0.31. Okay. So so I know both things here. I know the first cycle yielding will happen at D point, and the corresponding thing, the Sm is 442. Sa is 137, and the yielding will the fatigue at that load line, that at R, would be 211. So I have a factor of safety of 4. And now, can somebody tell me what will be the factor of safety for first cycle yielding? Any answers on this one? What will be my factor of safety for first cycle yielding? I'll leave up to you. You tell me. What will that be? What is my factor of safety for first cycle yielding? So this is where it happens, right at D point. What is my factor of safety for first cycle yielding? Can someone tell me that? None? No answers? How do I find out? How do I find out? You can check, but just a guess that is fine. How do I find a factor? Like I find the factor of safety for fatigue, right? How do I find this one for this yielding, for cycle yielding? Any guesses? I know this happens here, right? I know it happens at D, right? I know this happens at right D, right here, right? Now, how do I find it out? Some guesses. What will the easy guess? Somebody, at least I expect one answer, right or wrong, whatever. Using sigma m and Sm. Okay, you have SA and Sm because I am asking for factor of safety. So factor of safety has to include your loading conditions, right? It's very simple actually for yielding. It's very simple. You guys are missing something. I know my equation actually says sigma A plus sigma m is equal to sigma yield, right? For yielding, I used to use Langer relationship. And from Langer relationship, sigma y is equal to, or Sy is equal to sigma A plus sigma m. So what is the factor of safety? Any answers now? I've given you the entire hint now. So factor of safety will be very simple, just Sy, yield stress divided by sigma A plus sigma m. That's it. So it will be, let me just go ahead and just type it out here. So this I have SA by Sm. My factor of safety N yield would be very simple. It will just be Sy divided by sigma A plus sigma m. That's it. So this is my factor of safety for yielding, 5.62. Because my yielding will happen. Sorry. Okay. Looks like I have been disconnected for some reason. Can you folks hear me still?
We can hear you, sir.
Okay. So let me, but my screen is frozen, right?
Yes, sir. Your screen is frozen.
Yes, sir. Your screen is frozen, sir.
Yeah, let me do this. I think. Just 1 second. I think it should be fine. Just 1 second. I think there is some connection issues. Let me do one thing. Let me just try to disconnect and join back again. Okay. Looks like it is slow, but it is working. So I'll not mess it. Okay, I think it is back. So this is what I wanted to show you right here. So basically I wanted to show you that safety factor against yielding is very simple. You know when it yields. So the relationship between yielding and so if in basically Sy is sigma A plus sigma M. I have a sigma A plus sigma M, and factor of safety against yielding is just Sy by sigma A plus sigma M. So I have a fairly high factor of safety against yielding, 5.62 to be precise. Okay. Now I have to do the same thing for now ASME elliptical, right? So what do I need to do with the ASME elliptical? Nothing. Very simple again. I need first the intersection line, right? First I need to find out what will be the, let me just delete this. And I need to find out what will be the factor of safety with ASME elliptic. With ASME elliptic. So ASME elliptic, if I go ahead and show you what the equations you use, ASME elliptic is this factor of safety. So let me just go ahead and show you how it looks, the equations. ASME elliptic factor of safety looks something like this, right here. This is the ASME elliptical factor of safety. 1 divided by sigma A SE square plus sigma M SY square. So go ahead and let's just find out what will be the factor of safety here. This is the factor of safety. Let's just plug in and see what the factor of safety is. 4.21. So with Gerber, I was getting 4.11. With this, I am getting 4.21, fairly close. Can we check what we get out of, what is the factor of safety we will get out of modified Goodman relationship? I should get lower factor of safety, right? Let me just check what I am getting out of modified. How do I check for Goodman relationship? Right here. NF is this relationship. Let me just go ahead and punch in that relationship right here. Sigma A by SE, sigma M by SUT. Let me just go ahead and do that so that we know in all three conditions what do we get. So that would give us some handle. I'll just modify this NY here. So this should be sigma A by SE and sigma M by SUT. Sigma A, let's just plug in sigma A by SE, sigma A divided by SE, oh sorry, capital S small e, and sigma M divided by SUT, right? Is that correct? Sigma M by SUT. SUT. And this will be 1. And this will be NG. Let's see what we get. 3.39. So if I use, so if I were to use these three designs, ASME elliptic. So ASME elliptic is giving me a factor of safety of 4.2, right? So this is giving me the most reasonable estimate. Then Gerber is giving me 4.11 factor of safety. But if I use this design, if I use modified Goodman, I'm getting only 3.39, right? So I'm over designing. If I'm using this relationship, I'm over designing my entire fatigue life, right? And same thing we can do for all conditions, right? You can also do it for yield line. So yield line you get 162, and then you can also find out what will be sigma M from there. So basically same thing what we did for what is it called? We did for Gerber. We can also do it for ASME elliptic. But what I wanted to show you in a nutshell was that either of the relationships I can use. The only thing would be I as a designer would not want to over design, right? Because it costs money. I don't want to over design, but at the same time, I want to understand, and the design should not fail also. So I had to use an optimal design criterion, and ASM elliptic seems to be the most reasonable one, right? You're not over designing it by much. So that's the moral of the story with this. Let me give you another problem, which is a very interesting problem. So I'll actually solve that, and then we'll take some questions. Let me show the other one so that we finish that, and then we'll move to the other one. So other question is here. I have a steel bar that undergoes cyclic loading, right? So just sigma max is equal to 420, sigma min is equal to minus 140. For this material, SUT is 560, SY is 455, and fully corrected. I'm not giving you any corrections here. My fully corrected endurance limit is SE 280 MPa, F is 0.9. Now estimate the number of cycles to a fatigue failure using modified Goodman criterion. So what should be my first step in this? This is what I want to find out. So first thing is, what should I do? What will be the first step here in this problem? Tell me the first thing what we should do in this problem. I should find out first is the factor of safety. What is my factor of safety for modified Goodman? Let's find out factor of safety for modified Goodman. Let me go to my Mathematica and find out what is the factor of safety for modified Goodman. These are the equations, these are the relationships which I have in my problem. It told me that SUT is 560, yield is 455. It told me fully corrected endurance limit is 280. Sigma max is 420, sigma min is 140. So all I do is I find out sigma A and sigma M. This is my alternating, this is my amplitude component, and this is my mid-range component. So I just go ahead and do it. My mid-range component is 280. This is 140. So let me find out the factor of safety for modified Goodman criterion. Let's see, what do I get? I get 4 by 5, or if I want to find out what is the numerical value of 4 by 5, it's 0.8. What does 0.8 factor of safety mean? Now answer me this. What does factor of safety of 0.8 mean?
Failure.
What kind of failure? Yes, finite life. So it's not meeting. So if I am under that envelope, I can live up to 10 to the power 6 cycles. For this kind of a loading condition, I will not have infinite life. I will not live up to 1 million cycles. Now, how do I find out what cycle I can live? That's the question which I'm asking. What should I do? How do I find out what will be the number of cycles this can live? Now some answers. This is a bit more difficult than what I asked. So if I were to draw this, let me just switch little, and then you'll get a good flavor for this. I'll switch back here. Let me just show you this. So I will do this. Sorry. Yeah. Sorry. So this is it, right? So let me do one thing. First, let me just draw on this modified Goodman and Langer and just show you where it exists. So this is my sigma M. This is my sigma A. My Langer is yield. So this is SY. This is SE and SUT. SE and SUT. Let me put some numbers, right? SE is 280. This is 280, right? This is 280. This is 280. SUT is 560. And my loading condition is, if we, what did we get for sigma A and sigma M? I get sigma A is 280 and sigma M is 140. Right. What is my yield here? My yield is 455. My yield is 455. And SE is 280. So I am somewhere here. So this is my modified Goodman line. I'm somewhere here. 280 and 140. This is 280 and this is 280 and this is 140. 280, 150. 140, sorry, 140. 140. What this means is, if I were here, I would have infinite life. Since I am here, now I have a finite life. You get me? This one? Yes, a very good answer. How do I can use F? I can use that A and B relation, if you remember from there, right? A n to the power B. But to get A and B, I need a sigma rev also. Equivalent stress, equivalent reversible stress I need. Right? So how do I get this equivalent reversible stress? Sorry, how do I get this? This is the only thing. I can find out A and B. You know the formula for A and B. We had done it for finding the finite life. A n to the power B. But this is only for sigma rev. This relationship is only for a reversible, fully reversible loading. Now, how do I find out equivalent sigma rev for this condition? If I can do that, then I have everything. Any guesses here? Any guesses? How do I find out sigma rev from this condition? That's the only trick here. Everything else is fairly straightforward. The only issue which we have to figure out now is, how do I go and find out equivalent reversible stress? Sigma A is equal to 0. No. I have to use some relationship. Right. So let me just give you the Gerber relationship. So this modified Goodman relationship. What is the equation for this line? What is the equation for this line? If I want to find out the equation for the line for modified Goodman, sigma A by SE is equal to plus sigma M by SUT is equal to what? 1, right? I have to find out what will be sigma rev. So can I plug? So 1 minus sigma M by SUT divided by. So if I were to find out what would be a sigma rev, I can do sigma rev. It will basically come out to be, I can fudge that sigma SE is equal to sigma rev, right, for this condition. So I will have 1 minus sigma M by SUT is equal to sigma A by sigma rev. So I can say sigma A divided by 1 minus sigma M by SUT will give me some estimate of sigma rev from modified Goodman relationship. I can do this similar thing for different relationships. I can just fudge this endurance limit SE with sigma rev and get that thing. So let me just go ahead and reshare that thing to the other screen. Let me just share the other screen here so that we can solve it now. Okay. So now I have this relationship. Sigma rev I got now. Sigma rev I got from the same modified. I put SE. I estimated SE. Here. I estimated SE with sigma rev, and find out that there would be some sigma ref for which this relationship is correct. So do that, and I will find out this is numerical. Let me find the numerical values 373.33. So if I have 373.33 SE, if SE value goes from right now 280 to 373, this will have infinite life. That's what we did. Okay, and then I can find out what will be A, B, and N. So A is 907.2, B is minus 0.85, and I get 34,000 cycles as the life. So instead of having an infinite life, if I do this kind of a loading where my loading is outside the envelope, I get only 34,000 cycles as lifestyle, as life cycle. Similar thing you can do it for Gerber also. You can use the same relationship, replace SE with sigma ref, and find out. So if I use Gerber, then I get sigma ref as 298, and use the relationship, same relationship, and A and B are still correct, and I will get a 468,384 cycles as life. So just by using, so if I am using, so I wanted to say, I estimate the life 34,000 by using modified Goodman, and if I use Gerber, it's 468. ASME may be slightly better, more than this. So that's why I want to make it very clear that if I use this criteria, modified Goodman, I'm very, very conservative. Here I'm actually one order of magnitude conservative, right? Which is not good. So if I were to use, I would use ASME elliptic, which gives me more reasonable estimate, and I do my designs based on that. And you have to understand that with all that design, I still can have some failure, but mostly a good probability would always be covered. If I want slightly more reliability, I play with my reliability modifier a little bit and have a higher reliability. Okay. So I'll stop here. I think almost everything I have covered in fatigue. So this fatigue will stop here, and 5 minutes I will take question and answers if you have any questions and answers. Okay. Any Q&A on this? Anything that was not very clear, I'll be happy to answer for 5-10 minutes. So this is end of fatigue now. It has been totally covered. Whatever relevant things you need to understand, I gave you the concepts for the design criteria. I told you how do you have infinite life, when do you have finite life, when do you have yielding, when do you have fatigue. So all those basic concepts I've given you. So now what I want you to understand is, if you have any doubts, just come forward and I'll be happy to answer that. Okay, that's a very good question. Why did we replace SC with sigma ref? Now what I want is, under what condition it will have infinite life. So this SC which I have, right, gives me finite life. Right, and I know that I have to find out what will be the value where I'll get infinite life. So if instead of my SC being 280, if my SC were 373 or whatever we found out, right? What did we find out? 373. Then as per modified Goodman criteria, it would have infinite life. So I want to estimate at what SE you will get infinite life. That's why we replaced it. Because at 280 we are getting finite life. So we need to figure out, is there exists some value of SE where you will get infinite life. So that's what we plugged in, and that's what we got from here. Am I clear? So we wanted to find out for what SE you will get infinite life. That's what we wanted to find out. That's why we did that, all this juggling. Okay. So it has to be more than 280. What is that value? I estimated it using that equation. Any other questions? Any other questions, any other concerns? I'll give you a homework so you can reflect upon it, but feel free to discuss. If anything you have doubts, if any concerns you have, or anything that is a bit not clear to you, I'll be happy to answer that. Another thing I would have to ask is 21st, your project's first thing, your project definitions are due. You need to define your project, identify it, define it with some clarity, 2-3 pages, and that is due. So you have to start working for it if you have not started already. Okay. And the Wednesday after, we'll have the presentations for that. So Monday that thing is due, and Wednesday we'll start to have some presentations for various groups. So we'll try to finish it on one Wednesday, but if it does not, then we'll take the Wednesday after also. Not this Wednesday. Next week Wednesday after the report is due. Any other questions? Any other questions, comments, concerns? If not, I will stop the recording. I'll be there for a few more minutes. If you have any questions, ask me. If not, then have a great day.